All right, the next part is going to be about iterated integrals. It is going to be a bit long, so sorry about that, but it is crucial for understanding that there's going to be 4 examples of calculation of iterated integrals. Now, okay, so let's get with get on with the details. Now, we're going to see how a double integral can be expressed as an iterated integral. So, which essentially just like several single integrals. What do I mean? So I mean the following. So I mean uh, an iterated integral is something like this. So suppose that we have a function of 2 variables. Just as an example, let's say x times e to the x minus y. And then when we integrate it, say with respect to y, let's say as an example from -2 to 3. I'm not going to actually do it, but when you integrate it with respect to y for a fixed value of x, essentially what you get is some function of x, right? Some function of x, right? So if x is, I don't know, 3, you will get like one answer. If x is 2.5, you will get another answer, and so on. So the answer will be a function of it, will depend on x. So which means that essentially we can take this as a function of x, and then we are going to integrate it from, let's say, from 0 to 1. And by the after the second integration, we just get a number as a constant. Okay, so this is what an iterated integral really is. Now, so if f of x is a function of 2 variables, and so here is the picture. So it is defined for values of x and y that belong to some rectangle, and we assume that it is integrable over this rectangle. Then basically, what we can do, we can keep x fixed, right? And for a fixed value of x, if we consider the cross-sectional area, the slice area of our volume, then the slice area is going to be some function of x, let's say a of x. And then when we integrate it, as a function of x from well, A to B, then essentially it runs over the entire volume and we will get the whole volume. Right? So that's the idea. At the same time, we can express the area of such a slice as a single integral with respect to y. And this is what's going on here, right? So after this, we just take, well, the volume of every thin slice, add it up over the um, entire volume, and then essentially we get the integral from a to b dx, right? And this is the iterated integral, and this is basically the kind of the explanation behind the reason why the iterated integral is the same as the single integral, because by running these slices over the entire volume, we will just get the entire volume, right? So, and we can also switch the order of integration, and we can take slices with a fixed value of y and compute their areas and then add up over the entire volume. And of course, again, we will just get the entire volume. So this is going to be the iterated integral with in the opposite order of integration. And essentially, we will have 2 different um, iterated integrals. Right? So we can integrate with respect to y first and then with respect to x. So notice that here we are integrating with respect to y first and then with respect to x, right? So y goes first, then x goes second. And here x goes first and y goes second, right? So when you write dx dy, so the order on dx dy um, is the order in which we are integrating. So if dx dy, if it is dx dy, then we are integrating with x first and then with respect to y, right? So, and the limits of integration. So here the order is reversed, right? So from c to d means that so we are going to integrate with it from c to d second. and a to b, we're going to integrate with respect to, from a to b first, right? So here from c to d is on the left, from a to b is on the right, but it's reversed here. All right. So and that's basically what Fubini's theorem is. So Fubini, well, to be honest, so here it says that f is supposed to be continuous on the rectangle. It doesn't have to be. So if you, go to the Wikipedia page on Fubini's theorem, and it says that Fubini's theorem is correct. So the statement is correct if the double integral of r of our function f of x, of the absolute value of the function f of x over our rectangle is finite. So then Fubini's theorem is correct. And in that case, the double integral over the rectangle equals either of the two iterated integrals. So both iterated integrals are going to be equal to each other, and their values are equal to the double integral. All right, so enough of theory. So let us go through examples. So evaluate this double integral over the rectangle R, and R is this rectangle. So here x is from 0 to 2, and y is between 1 and 2, right? So what does it mean? So according to Fubini's theorem, it means that the double integral over R of our function x minus 3y squared dA is actually equal to the following. So x changes from 0 to 2. So I'm going to write from 0 to 2, and dx is here. Then y changes from 1 to 2. So y changes from 1 to 2 dy. And the function that we are integrating is x minus 3y squared. And so this is how we rewrite our integral as an iterated integral. Well, alternatively, we can just switch x and y. It's going to be the same thing, right? So dy dx is the integral that I just wrote down. Alternatively, you can rewrite it in the other in the opposite order of integration. So notice that you need to change the order of dx dy, and you also need to change the order of the integral symbols here. Okay, so what happens if we integrate with respect to y first? So it's going to be like this. If we integrate with respect to y, it's going to be the integral from 1 to 2 x minus 3y squared dy. The resulting function, we are going to integrate from 0 to 2 with respect to x. So how do we do this? So basically, we first look at this, the inside integral. So we are going to integrate this function with respect to y, right? So x now is a constant. So imagine that x is a constant. So its antiderivative is really x times y minus the antiderivative of 3y squared is what is y cubed, right? So y cubed. And we need to take the change of this function from 1 to 2. But since it has both x and y, I can find it convenient to write it from y equals 1 to y equals 2. Right? So to see that the change is really in the variable y, and x is now fixed. All right? So this really means first I substitute 2. So as y, so it's going to be x times 2 minus 2 cubed. So here y is 2. So here y is 2 minus x times 1 minus 1 cubed. So here y is 1. Okay, so this is how I compute the change. So now let me just do all the calculations. So it's going to be 2x minus 8 minus x plus 1, and this is really just x minus 7. Okay, so the inside integral is just x minus 7. And now I'm going to integrate this from 0 to 2 x minus 7 dx. All right, so when I integrate x minus 7 dx, so let me just show you a little trick that somehow I find it kind of more convenient to do integrals like this. So maybe you will, it's up to you how you do it, but I find more convenient to do it like this. So let me split the integral into two parts. One has x, the other one is just 7 from 0 to 2 x dx minus from 0 to 2 7 dx. Now, the first part, I am going to evaluate it just, like we normally do. So the antiderivative of x is x squared over 2. And then I'm going to take the change from 0 to 2. And this is really, I substitute 2 into x. So 2 squared over 2 minus 0 squared over 2. So this is 4 over 2 is just 2. And this part, I personally find it easier to factor out 7 times the integral from 0 to 2 of 1 dx. And the integral of 1 is just, it's just this number minus this number. So this is really 7 times 2. So you don't have to get into the business of finding antiderivatives, because the integral of a constant is just that constant times the upper limit of integration minus the lower limit of integration. So this is just 14. Right? So the final answer is what is 2 minus 14 is 2 minus 14, which is minus 12. All right. So this is how it goes, and here is the answer. So notice that we could instead integrate with respect to x first. So here is how we, so let me not, I'm not going to write it, write it on the screen. So let me just explain what's going on here. So it is exactly the same integral. So what changes is the order of integration. Instead of dy dx, we have dx dy. And of course, we need to change the order of these kind of limits of integration, right? So because first we integrate with respect to x, right? So first we take this integral with respect to x, and then integrating this with respect to x, we just basically take the antiderivative of this function. So it's going to be x squared over 2 minus 3x times y squared x. And we need to take the change of that function from 0 to 2. So notice that now we are integrating with respect to x, so changes in x. And then, of course, when we substitute all the values, we will get the same answer. Okay, now let me do a few more examples just to to understand it better. So find the volume over the given rectangle. So first of all, let me explain. Let me show you that this question makes sense in the sense that this z is going to be positive in the given rectangle. Right? So how can we see that z is really positive? Well, basically, z is what? Z is 4 minus the sum of x and y. And what is the largest possible value of x plus y in the given rectangle, right? So x plus y is maximized. Basically, to maximize x plus y, we need to maximize x and maximize y. The largest value of x is 2, the largest value of y is 1, right? So when x is 2 and y is 1. And in that case, the maximum of x plus y is really 3. The maximum value of x plus y is really 3. And in that case, z is going to be 4 minus 3, which is 1. So even when x plus y is the maximum, so which means that z is the minimum, it is still positive. So which means that z is should be always positive, because even at its lowest point it is positive, right? So z is positive for all values of y in the given rectangle. So which essentially means that this is indeed the volume. So the double integral of our function 4 minus x minus y dA is just our volume. So this is our volume. Okay, so how do we compute it? So let's just immediately substitute our limits for x. So from 0 to 2 with respect to x, and then from 0 to 1 with respect to y, 4 minus x minus y dy dx. So that's the integral that we are going to compute. Okay, so here is how we do it. So let me just rewrite the integral. So let me write it here. So the integral, from 0 to 2, then from 0 to 1, 4 minus x minus y dy dx. So first, let me do the inside integral. And again, so I find it convenient to kind of split it into two parts. So one that has y, and the other one that does not have y at all, right? So this is going to be really the integral from 0 to 1, 4 minus x dy minus the integral from 0 to 1 y dy. So why do I think that this is convenient? Because I can take this and take it out. So it's going to be 4 minus x times the integral from 0 to 1 dy. Since we are integrating with respect to y, so anything that just has x is really a constant, minus the integral from 0 to 1 of y dy. So, and this expression, the integral from 0 to 1 of dy is just 1 minus 0, which is 1. So this is really 4 minus x times 1, which is just 4 minus x. 4 minus x, sorry. 4 minus x. Okay, so, and we need to evaluate this part, and this part is, so let me rewrite 4 minus x minus, this is the change of y squared over 2 from 0 to 1, and this is really 4 minus x minus 1 half, which is 3.5 minus x. All right, so this integral is 3.5 minus x. So which means that the whole expression is going to be the integral from 0 to 2 of 3.5 minus x dx. And again, so we can split it into two parts. So the first part is 3.5, the integral from 0 to 2 dx, minus the integral from 0 to 2 x dx. And this part is easy to compute. It's just 3.5 times 2 is 3.5 times 2, which is 7. And this part is, well, is really the antiderivative of x, which is x squared over 2, and the change from 0 to 2, which is really 2 squared over 2, which is 2. So what we get is 7 minus 2, which is 5. So that's the answer. All right, so this is the answer. Okay, find the volume of the solid that lies above the square and below the elliptic paraboloid, whatever that means. You don't really have to know what this means, elliptic paraboloid. I guess you can figure out that, again, so the possible kind of the largest values of x and y, I mean, we are subtracting x squared and y squared, x and y are positive, so in order to minimize the difference, we've got to maximize the term that we are subtracting, and the minimum is attained when x and y are as large as possible, and the largest possible values are 2 for both x and y. So the smallest value of z is really 16 minus 2 squared minus 2 times 2 squared. Um, so 16 minus 4 minus 8, which is still positive, right? So we see that z is really positive. So which means that we can just compute our volume, in the usual manner. Maybe just for your information, this is what elliptic paraboloid looks like. So we are talking about something like this. Now, when I plotted this in Google, I didn't really restrict x. Well, here x is from negative 10 to 10. I'm not sure if it's possible to change it from 0 to 2. Oh, apparently it is possible. Okay. No. Okay. Probably it's not possible. I don't know. But it kind of, it is something like this. All right. So which really means that what we are going to do is the integral from 0 to 2 by x, and the integral from 0 to 2 by y of 16 minus x squared minus 2y squared dy dx. Well, it doesn't really matter whether we do x first or y first. It's going to be the same thing. So let me just quickly do this. So the inside integral with respect to y, and again, so I can take this out. So this is going to be 16 minus x squared times the integral from 0 to 2 dy minus 2 times the integral from 0 to 2 y squared dy, right? So this part is just 2 times 16 minus 2 times 16 minus x squared, which is really 32 minus 2x squared. And we need to look at this part, and this part is the 2 times the change of y cubed over 3. This is the antiderivative of y squared from 0 to 2. All right, 2 cubed is 8 times 2 is 16, so this is just 16 over 3. So the whole thing becomes 32 minus 2x squared minus 16 over 3. Well, I guess I can just keep it like this for a while, so maybe it's going to become easier to simplify later, right? So I'm going to just keep it like this. So notice that this is a function in x, and we need to integrate it from 0 to 2 with respect to x, right? So we will integrate this from 0 to 2. 32 minus 16 over 3 minus 2x squared with respect to x. And again, so this part we can just take out, and the integral is from 0 to 2, so we'll get 2 times 32 minus 16 over 3 minus 2 times the integral from 0 to 2 x squared dx. All right, so this part is really minus 2 times the antiderivative of x squared is x cubed over 3, and the integral is taken from 0 to 2. So this is minus 2 times, and again, this is like 8 over 3. So this is minus 16 over 3. Right, so overall we get the final answer is going to be 2 times 32 minus 16 over 3 and minus 16 over 3. And now you see it kind of becomes easier, because it's 2 times 32 is 64 minus 2 times 16 over 3 minus 16 over 3. But this 2 times 16 over 3 and 16 over 3 is really 3 times 16 over 3. So this part is really 3 times 16 over 3, which is just 16, right? So the final answer is going to be really 64 minus 16, which is 48. This is how we can do. All right. Okay. So apparently the um, printed answer provided is in the opposite order instead. So here we are integrating with respect to x first. But I guess it doesn't really matter. Well, and in the printed version, so they do not do the district when we factor out the constant first, and then we just deal with whatever remains. But it's really up to you, whatever you prefer. So this part and this part, I would really just take it out and multiply by the upper limit of integration minus the lower limit of integration. I just find it easier. But if you want to integrate constant like properly, finding its antiderivative and finding the change, it's really up to you. You can do it. Okay. Now example 5. All right. So example 5. Now basically when we do this, we have a choice of really. So we can rewrite it as a double integral y sine xy dy dx versus the double integral of y sine xy dx dy. Right? So if I are integrating with respect to y first, so this is y, this is x. So then y is changing from 0 to pi, and x from 1 to 2. If we're integrating with respect to x first, then x changes from 1 to 2, and y changes from 0 to pi. Right? And unlike in the first three examples, so here the order of integration actually matters, because which integral is easier to calculate. So which, I mean, is it easier to find to compute this integral or this integral? So I noticed that if you're in the first of them, you will integrate something like y times sine of y again with respect to y. So which really means that you will have to do integration by parts. While if you do this integral with respect to x, then there's no x in front, and you can just do it directly, which means that it's just easier to do the second integral, right? So what I'm trying to say here is that if you just pause and look at it for a moment, then you will realize that the second way to do this seems to be much easier. So let me just do the second way, and you will just read how to do the first way from the printed slide. So the second way is like this. So from 0 to pi, then from 1 to 2, y times sine of x y dx dy. All right, so let me do this. So here I can't really do, I mean, I could do the trick with factoring out the constant, which is y, so I can take it out, but here it doesn't really help. I mean, so what is the antiderivative of sine? The antiderivative of sine is minus cosine, right? So the antiderivative of this is minus cosine of x, y. And I will probably have to multiply by some function in y, but let me just do this. So let me just find the derivative of this function with respect to, I'm integrating with respect to x, so I'm going to differentiate with respect to x too. So minus cosine of x, y. So the derivative of cosine is minus sine, so the derivative of minus cosine is sine. It's going to be sine of x, y. Well, strictly speaking, I should talk about partial derivatives. Well, because there are two variables. And times the derivative of whatever is inside with respect to x, which is y. So notice that what I got here is exactly my integrand, right? So, which means that's already my antiderivative, and I don't really need to multiply by anything else. So it's just the answer. Okay, so this is the antiderivative. So, and I've got to take the change of this antiderivative from 1 to 2. But you've got to be careful because there are two variables here. So it is better to kind of remember that we are integrating with respect to x. So it's the change in respect to with respect to x from 1 to 2. All right, so this is really when x is 2, I get minus cosine of 2y minus cosine of x is 1 is just y, right? So what I get is really minus, well, minus and minus is plus, so it's just cosine of y minus cosine of 2y. Okay, so my integral is really just the integral from 0 to pi of cosine of y minus cosine of 2y dy. And here I've got to just do the antiderivative. The antiderivative of cosine is just sine, so sine y minus 1/2 sine of 2y, and I've got to change the change from 0 to pi. But notice that it's going to involve substituting y, substituting 0 and pi for y, but sine of 0 is 0, and sine of pi is 0, and sine of 2 pi is also 0, so the answer is just 0. It's very simple. Okay, so and this is how we can work it out. But notice that if we reverse the order of integration, then we will have to use integration by parts. And we can do it, it's kind of doable, but it involves a lot of unnecessary complicated computation, right? And this is, you know, the inside integral that we, evaluate by parts. And after this, we still need to integrate it one more time, from 1 to 2. And again, so it cancels out, but unlike in the first method where all the individual terms were just 0, so here, and it was kind of easy to see immediately. So here it's got some x squared, and we really have to substitute, plug it in, and to see that it still is 0. All right, so that's the end of this part. Sorry, it was very long, but I hope you don't mind.